This video is about measuring the resistance of thermistors at different temperatures. It corresponds to sections 8.3 and 8.4 of the Applied Analog Electronics textbook. The Chapter 8 is Lab 2, the thermistor lab. Okay, so the thermistors that we'll be using are these little black epoxy-coated ones, and the epoxy coating means that we can dip them into water without destroying them. Now, the leads here do not want to get into the water. You do not want the metal parts getting into the water, because then you'll have a short circuit path through the water itself. And if you're using ordinary tap water, it is somewhat conductive. So we're going to want to have this thermistor dipped just far enough into the water that the head of it is completely wet, but the tails out here that we're connecting to remain dry. We're going to want to measure the resistance, so we have to connect some alligator clips up to that. And we're going to want to know what the temperature is of the water bath we're putting it in. So we're going to have a thermometer to measure that temperature. Now, this thermometer is one that I particularly like because it has this calibrate button. I mean, it's a cheap kitchen thermometer, but the calibrate button makes it as good as many of the lab thermometers that are 2 or 3 times the price. The way you use the calibrate button is you put the thermometer into 0 degrees C water. How do you get that? You melt ice in the water. Now, you don't want the tip of the thermometer touching the ice, because the ice may be much colder than 0 degrees C. But once you've got the water down to 0 degrees C, it's pretty accurate, as long as you haven't got a lot of salt in the water or something. It's a pretty accurate 0 degrees C. And press this calibrate button once the thermometer has reached the same temperature as the water, and it'll subtract off its current reading and give you 0. And so that makes these thermometers pretty accurate at low temperatures, and not too bad up to boiling temperature, which is as hot as we can take these thermistors we've got anyway. So, nice little kitchen thermometer, and quite usable for the sorts of work we'll be doing. Okay, so we're measuring the temperature with one, and we're going to measure the resistance of the other, but we really want to be measuring the resistance of this thermistor when it's at a known temperature. So what we're going to do is we're going to connect these two together mechanically, so that they're going to be at as close to the same temperature in the water bath as we can make it. And it's the end here that is where it's supposedly most sensitive, so we'll just tape those two things together. Now, you may have noticed in looking at this thermistor that the two wires here are not the same length. That's because the wires are very fragile and break easily. And if you just hook clip leads up to them right like this, you're likely to break one of the wires. In fact, this is not the first time I tried recording this video. I've broken that wire trying to record these videos. So what I want to do is to provide some strain relief so that the alligator clips that I've got here don't pull on those wires and break them. And I'm going to try to do that the way I tried a few minutes ago, by taping the wires to the shaft of the thermometer. And the difficult part here is often to keep the alligator clips from shorting to the body of the thermometer. I am having a little trouble with this alligator clip. The wire is smaller than this alligator clip likes to close down to. All right, there is that one. And It just pulled off. The black one just pulled away from where it's supposed to be. Alright, let's see if we're getting good electrical connection there by using the ohmmeter. I've got the ohmmeter set for 20 kilo ohms and it says 8.57 or 8.58. That sounds reasonable since we were expecting 10 kilo ohms at 25 degrees C. Well, what temperature have we got this thing at? Let's turn it on. And it's about 28.4 degrees C. 28.5, 28.6, it's a little warm. And so the resistance is a little lower than what we would expect at 25. Alright, now what I'm going to do is take a thermos and put some hot water in here. Now, I really like doing this thing in the kitchen because then I can have access to water that's actually boiling or ice water, but I don't have a video set up in my kitchen. Now, one of the things that's difficult here is you don't want this to touch the bottom of the cup because the cup is a different temperature perhaps from the water bath. And you don't want to have to hold it because you're going to have to be sitting there typing these numbers. You want to measure the temperature, the resistance at the same time. And so I've just used a clothespin here to hold it over the top of my coffee cup. And one way to get a lot of measurements is as this water cools down, as soon as that gets to 82 degrees C, there, it was 1.82 at that point. So 1.82 kilo ohms. In fact, now that if I'm below 2 kilo ohms, I can actually measure a little bit more precisely here on the 2 kilo ohm scale. And so when it just went past 81, I should have, when it went past 81, looked at what the resistance was here and typed in those pair of values. And so you're going to want to get basically almost every degree C from 100 degrees C down to 0 degrees C. You probably won't be able to hit quite 100, quite 0. The temperature changes very abruptly as you put it into the cup. So you may not be able to get above 98. You may not be able to get below 1. And now I have to switch to the 20 kilo ohm scale because I've gotten above 2 kilo ohms. And so record the temperature and the resistance. If you're working in pairs, this becomes a little bit easier because one person can be calling out this moment that hits the particular temperature. Like as soon as it gets to 77 here, they could say 77. In fact, 76.9. It went 2 steps at once. And the other person can be looking at the ohmmeter and record the resistance at the exact time that the temperature there changed. When you're working alone, you have to do tricky things like, here I used a clothespin to hold the thermometer and the thermistor in place as the thing cooled down. Now, you're not going to be able to get below room temperature with this thing of putting in boiling water and watching it cool down. In fact, it takes a long time even to get to room temperature. What you're probably going to want to do is once it's cooled down and it's cooling very slowly, you could lift the thermometer out, stir in a little room temperature water, put the thermometer back in, and record a bit there. So mixing water to get different temperatures. But do mix it afterwards because if you've got a lot of different temperatures in the cup and you have convection currents and stuff like that, the thermistor and the thermometer may not be at the same temperature. If they're a degree or so off, that's going to throw off your measurements. So make sure that your temperature in your water bath is fairly well mixed. To get temperatures below room temperature, you're going to need ice. So start with ice, but don't let the thermistor or the thermometer get in contact with the ice because the ice may be below 0 degrees C and you'll have a very big difference in temperature. And if you have ice melting in your water, then you'll have convection currents from the cold water as it comes off of the ice. So fish any ice out of your water after you've got it down close to 0 and let it warm up to room temperature. And again, once you start getting close to room temperature, it's going to move very slowly, and you might need to mix in little bits of warm and cold water in order to get the temperatures you need. I recommend that as you make these measurements, type them directly into a file and use GNUplot to look at that file. Save it every once in a while and take a look and say, oh, I'm missing some things around 35 degrees C. It's now 71 degrees C. Cool it down, look at the stuff around 35 degrees C. Oh, when I did this thing, I got two different measurements here at about the same temperature that are way different in resistance. I probably typed one of them wrong. Let's redo the experiment in that range until we've got the clerical errors all removed from the file. So look at your data as you collect it. Make sure you don't have any gaps in your data, that you've gotten to the ends of the range as hot as you can get and as cold as you can get. One trick for getting hotter temperatures: preheat the cup. Fill the cup with boiling water, let the cup get up to temperature. The water is no longer boiling. It's cooled down quite a bit. Dump that and put new boiling water in. Now the cup was up around 95 degrees C. The boiling water won't cool nearly as much going into a hot cup as it went into the room temperature cup. Same thing when you want to get really cold, pre-chill the cup with ice water. Once the cup is nice and cold, then fish the ice out and you've got cold water. Okay, feel free to play around with different ways of holding your thermistor, of putting the clip leads on it. You're going to need something so that you can work on this thing pretty much hands-free though. Okay, you'll get probably slightly different temperature and resistance values than I'm getting here. These meters are not that repeatable. The thermistors are not that repeatable either. So expect to get some differences. If you get exactly the same numbers as I'm getting, it's actually a little suspicious. Okay, have fun with the lab.